So, Panama. This talk is about Project Panama and about all the work that we put over the last few years. Panama is another of those projects like Valhalla that we talked about yesterday that started many years ago, almost 5. And it feels like we've done a lot of progress, but still we are not in a stage where we can actually ship some deliverable. And so in this talk, I'm going to talk about a little bit of this soul searching that we've been done over the last year or so in order to try to tease apart some of the Panama features and try to get to some deliverable faster. As a reminder, I work for Oracle. Take everything I say with a pinch of salt, of course. And where does Panama start from? Of course, Panama starts from a reality check that not all the libraries that people want to use are written in Java. There are libraries, for example, if you want to do off-CPU computing that are written in C or C++, and you want to access them from Java. And the way to do that today is using JNI. JNI is not bad in the sense that it works, but as I'm sure most of you in this room know, JNI has a lot of issues in the sense that it's not a very usable framework. In order to make it work, you have to write a lot of native code, native glue code, in order to be able to call the native library that you actually want to access. And that sometimes can lead to native libraries going out of sync with all the glue code that you are trying to write. And the result is something like this. So often native libraries tend to go out of sync with the JNI interfaces that are implemented. So if you go on the TensorFlow page, you click on Java, there will be a banner there that says, oh, by the way, this API is not fully covered by the stability guarantees of the TensorFlow API. How do we solve this? Well, Panama wants to maintain the simplicity for developers in accessing native libraries. And in fairness, native methods are not hard to use for a user once somebody made the JNI bindings available to them. But Panama wants to dramatically improve in the ease of generating native bindings. And the idea is that if bindings are easy to generate, and if you have tools to generate them, then there will be more bindings available to Java developers, and there will be more Java developers actually taking advantage of the great libraries that are out there that may not be written in Java. So the motto of Panama is essentially lowering the barrier and the impedance mismatch between Java and native libraries. So as an example, TensorFlow. TensorFlow is a big library. It has 160 functions, 23 structs, and I'm talking about the C API. And if you go inside the GitHub repository, don't take my word for it, if you go in the Java branch, there are almost 4,000 lines of code, native code. So this is all native code that you have to write in order to be able to actually even use the TensorFlow library in the first place. So this is all native glue code that you have to write. And then there are also some 7,000 lines of Java code. Some of that may be related to JNI methods, some of those may not. You can imagine how many engineering effort have been put in order to write this code. With Panama, you replace all of that by using a single tool called jextract. You point jextract at the header of the TensorFlow library, and then you pass some magic incantation of compiler flags, as normally people will have to do when working with C. And what you get back is a jar file. This jar file will contain some interfaces with some annotation that the Panama runtime understands. And once all these classes are loaded, then you will have a fully functioning Java bindings for TensorFlow. And so you can just add the jar file to your class path and start using TensorFlow. So you can ask TensorFlow which version it is, and that just works. So we basically replaced a process that was requiring many engineers, many weeks of work, with basically 5 minutes of figuring out what were the actual correct parameters to pass to jextract. And that's actually the value that Panama provides. So using Panama is easier because there's less stuff that you have to write in order to make things work. And since there's less stuff that you have to write, there's also less chance for things to go out of sync. So it's also safer because all the native code, all the native glue code that you would have to write now is generated dynamically by the VM based by the metadata that has been produced by jextract, so there's no chance for things to have bugs in a way. So you can't introduce safety problems by writing bad native code in there. Panama is also faster because now there's no intermediate layer between your Java program and your native library. And so the VM has a greater knowledge of the fact that it's about to jump into some native code. And so the JIT can optimize this call site much better than it used to do with JNI. And so Vladimir spent a lot of cycles into creating an alternate backend for Panama called link to native, and the numbers for link to native are really impressive. And we're talking about 4x, 5x improvement for both calls from Java to native and native to Java. So that's pretty good. So the natural question here is, are we there yet? This looks pretty good, right? Are we ready to ship something here? Well, that's a question that I asked myself several times over the last 2 or 3 months, perhaps obsessively. And I always go back to what is the audience that will benefit the most from Panama? And I think I isolated 3 groups of developers that will benefit from some of the things that we're doing. The first group is, of course, library users, people that want to use TensorFlow. And these people, yes, they are getting some advantages by using the Panama approach. I don't think maybe their life will be dramatically different. They will probably be equally as happy as with some JNI binding, but we are not doing worse than JNI, so that's good. Then there are the library developers, so people that want to produce those bindings. And people that want to produce binding, they don't care too much about usability. What they care about is how easy it is to generate bindings and how easy it is to maintain them after they have been generated. And I think in this case, Panama is essentially blowing JNI out of the water. And then there's a third category of users, which are basically all of you in this room. So people that write frameworks. And we know from past years that there are people like Charlie Nutter that write frameworks such as JNR, or Samuel O that is writing frameworks such as Java CPP. There are already stories, end-to-end stories for providing rich interop between Java and native code. And what these framework developers are looking for is not a way to produce bindings automatically. They basically want some building blocks that they can use, maybe to take advantage of some of the optimizations that we put into the VM. And Panama is not doing too well in this respect. There are not many primitive building blocks that you can find inside Panama. Everything is very monolithic at this stage. So it feels like we kind of missed an opportunity here. Yes, usability is fine, but yeah, it feels like something is missing. There are not many things that we can reuse. Well, in Insight, that is kind of the consequence of the way Panama has been developed over time. We had to do everything, and so at the same time we were working on the plumbing, so on trying to basically tweak the VM, add support for generalized universal native calls, and at the same time we're also working on the tooling story and the higher level C-interop layer in order to basically make it all work. So it's not a surprise in a sense that we didn't come out of this exercise with some solid and stacked layer and beautiful design that we can then expose to some other framework. So if we want to build a more solid Panama house, we need to start from solid foundation. And what actually are the building blocks that we're looking for here? One first naive, maybe, assumption is to essentially assume that the building block that we are after here is foreign function calls. So that's after all what Panama is about, right? We want to be able to call stuff that is inside the native library. So what about modeling a native function as a method handle? Method handle represents a unit of execution, is very good at doing that. So why don't we expose a very low-level API that allows me to capture a foreign function as a method handle? And in fairness, we did that last year. We isolated a very small API, a very small core inside the foreign Panama branch that allows you to essentially view a native call as a method handle, and also to translate a method handle as an adapter that can be used as a function pointer, so for up calls. And this works up to a point. So it works well if your native call is only dealing with primitive types. And that's because essentially Java carriers are good enough for expressing all the primitive types that there are in native functions. But as soon as your functions start accepting structs or pointer to structs, things get a lot more messy, because then you need some system, some way to move data in and out of the function. So essentially you need some way to create data of heap. So surely there must be a way to create data of heap, right, in JDK? There is something. You can use ByBuffer, as we were saying yesterday. You can create a direct buffer, and you can allocate stuff of heap, and then you can get and put bytes, and that kind of works, but it has limitation. A ByBuffer is an API that has been designed after I/O, so it has limitation in the addressing space, 32 bits. It has limitation in the way in which the memory is deallocated is very non-deterministic. It's essentially GC driven. Of course, as you can see from this slide, there is a long request of enhancement for the ByBuffer API. These requests are not really requests for enhancing the ByBuffer API. They are really trying to ask for a different API to do all this stuff, I think. Then you can always switch to the dark side and start programming with Unsafe. Unsafe is very powerful. It's probably the most efficient API out there for doing off-heap access, because it takes advantage of the VM intrinsics. The problem is it's unsafe. So you can crash the VM. You can, maybe Unsafe is going to be moved somewhere else, so your program is going to not be able to find Unsafe anymore. Or, well, anything can happen. So really, the people I talked to last year at Oracle Code One and other conferences, they weren't too adamant in going down this path. They wanted something they could rely upon, some public API of some sort. So they typically prefer the ByBuffer approach. So what about Panama? We were talking about Panama as a way to bridge the gap between Java and native libraries. So Panama has, in fairness, a pointer API. There are good things about the pointer API and bad things. The good things is that it replicates the behavior of a C pointer pretty well. So every Panama pointer has a type, like in C, every pointer has a type. It uses generic to keep track of the type. And the type of a pointer affects the semantics of operations such as offset and things like that, and even the reference operation. The bad thing about pointers is that they are C pointers, so they are typeful. So if you want, for example, to use the pointer API as an heterogeneous buffer, to model an heterogeneous buffer and start to pick and poke values into that buffer, you suddenly start running into problems, because you have to cast the type to byte, and then to move the pointer to a certain offset in bytes, and then to downcast the pointer again to the type you wanted to use for the reference operation, and you have to do that for all the operation that you need to do on your buffer. So, no, not good enough. That's essentially, yeah, the situation we're in. So what we learn is that in order to do native calls, we need some way to move data in and out of functions. So maybe moving data is the missing primitive that we were looking for. And that was kind of an happy thought, because after we realized this, we started to think, well, actually, there are a lot of other use cases, interesting use cases, that couldn't care less about calling native function. They only care about maybe serializing some object graph of heap for caching or other purposes. There are a lot of frameworks that do this. I spoke with a lot of my colleagues doing machine learning. They are interested in modeling tensors of heap. That kind of stuff is not captured by any API we have in the JDK. So we have reason to believe that foreign memory access is actually the main missing block that Panama has been looking for all along. And if we have that, then we can build all the higher interop stories on top. So we can build a system API interface that provides access to native function with method handles, and we can have jextract and the C pointer API on top of that as well. So we can deliver that in stages. So I hope I have convinced you that we need a memory access API. So let's start to look at what's inside this API. The goal here is to have a general API that works on basically any memory sources, on heap, off heap. I called it foreign memory access API. And it has to be safe and efficient. By safe, I mean that it should not crash the VM, ever. And efficient, well, it should be, by efficient, I mean that it should be as fast as unsafe. That's kind of my target. It's an ambitious target, as we will see later. The goal eventually is to replace all the usage out there of ByteBuffer and Unsafe that are trying to use those APIs or distort those APIs in order to do off-heap access, and to use a proper API replacement for that. There are three key abstractions in this API. One is memory segment. It's a contiguous region of memory that has spatial and temporal bounds, and we shall see later what that means. Then we have memory addresses, which are simply offsets into a segment. So not much about that. And then we have memory layouts. Layouts are just the optional description of the contents of a segment. You can use them if you want. You get some benefits in doing so, and I'll try to show you what the benefits are. For the referencing memory, we didn't invent a new API. We just rely on PO-grade variable API because that has all the primitives that we want. It has support for CAS and things like that. So it's just the right API. We don't need anything better. This is a low-level memory API, so we are not trying to build a very high-level story here. So this is what a segment looks like. I use the C syntax to kind of describe the layout of the segment a little bit better. So it's, we have a start point with two coordinates, x and y. We can assume that the coordinates are 4 bytes each. And then we have an array of them. We have 5 of them. So we have all the coordinates laid down, x0, y0, x1, y1, and so forth until x4, y4. As you can see, there are spatial bounds here at play, because a segment naturally implies a base address, so the start of the segment, and the limit address, the end of the segment. If you have an address, like at the base address, for example, you can move it. You can create a new address at a new offset. So, for example, I can specify an offset of 4 and move the base address into a new address that, instead of pointing to x0, points to x2. And with the segment, I also can do another trick. I can take a segment and I can slice it down. So I can create a subsegment whose bounds are contained into the original bounds. And when I do this, I'm not copying memory or anything. I just create another view. And this is especially useful if, for example, I'm implementing an allocator. So I have a big slab of memory, and then I just want to hand over chunks of memory to different clients, and I don't want this client to interfere with each other. So that's very good. And once we have values, this can be a value type, so no allocation. So that's pretty cheap. As I said, for the referencing memory, and this is kind of the hardest part maybe of the talk, because we have to understand how you actually get values out of memory and how you put values into memory, you need to obtain a variable. We call this variable memory access variable, without a lot of fantasy maybe. And with a variable, of course, you need a carrier type, because the variable is always going to deal with it's going to give you value with a certain Java type. And all the types we support for now are the Java primitives minus Boolean. In the future, we may support even more carriers, like we saw yesterday for the vector API, so we may even support half floats or int 128 or something like that. Every memory access variable has one mandatory access coordinate type of type memory address. So in order to be able to dereference memory, first you have to tell the variable what is the address at which you want to dereference memory first. Then if you want to get fancy, we have also a set of combinators that you can use in order to view a flat buffer of memory as a multidimensional matrix that you can access with indices. And I'll show you how that works. It's probably better with some pictures. So as I said, first step, obtain a varhandle with some carrier. So the way you do that, you do memory handles dot varhandle, and you pass the carrier type that you want. So if I pass in .class, I'm gonna essentially create a varhandle that is gonna read the contents of memory in 4 bytes, and it's gonna give me a Java int, for example. So if I pass the base address, for example, I'm gonna get x0, viewed as a Java int. What if I wanted to get y0 instead of x0? Well, there are 2 ways to do that. One is I can take the base address and move it of 4 bytes, and then I can use the same varhandle that I have now, or I can create a new varhandle, a varhandle that has some displacement, some static displacement attached to it. So what this varhandle will do is it will take the incoming address, offset it, and then do the dereference at that particular address. This is useful because I can keep my varhandle static, and I keep my memory address static, and all the computation will be done inside the varhandle, so it can be optimized very well by the JIT. Then another trick, what if I wanted to access all the y coordinates in this array? That's when we need to use the powerful higher order combinators that basically add an extra dimension to our varhandle. So if I add a stride, I can basically tell the varhandle how much apart my elements are, and then the varhandle will also accept a trailing long index that I can then use in order to specify which of the y coordinates I want to obtain. And this is pretty powerful. We can keep combining this with multiple stride and multiple offset, and we can start accessing data inside matrices with multiple level of nesting. As I said, it's not just about spatial bounds. There are also temporal bounds. A temporal bounds means that essentially a segment is created, then it's used, and once it's not used anymore, you have to close it. So you have to signal the runtime of the memory access API that you no longer use the segment and the memory can be freed. So this is very different from ByBuffer. This is essentially deterministic the allocation. We want the programmer to be in charge of when the memory has to be released. Of course, with power comes responsibility. So if you forget to call the close method, you can induce some memory leaks, because if your memory segment becomes unreachable, then there's no way for you to call the close method. That's a problem that also the netty-bybuff API has. I know they have some agent that allows you to find some memory leaks that are lurking in your code, but I think it's a pretty good trade-off. I think having determinism is way better than not having it, and having some guaranteed absence of memory leaks. So this is how you work with segments. So this is an end-to-end example. We essentially want to set a bunch of numbers into our array of point. So first we have to create the segment, and we do that using one of the many factory methods provided by the memory segment API. In this case, we want to create memory of heap, so we are going to use the off-native factory. There are also other factories that allow you to create a segment from Java heap arrays and even from bybuffers. So we have to specify a size in bytes of the segment. If we wanted, we could also specify an alignment. So if we wanted to create an hyperalign segment, we could do so with this API. And then once we created the segment, we can use one of the 2 varhandles for accessing all the x and all the y's. Those are constructed in a very similar way to the one that I showed you before. And then, so we can set all the x elements inside the loop, and then all the y elements. And then when we close the try with resources, the memory will be free. So this is very good, it's very expressive, but there are some issues with this code. And all the constants that are present here are all places for the bugs to hide. I have a bunch of constants for the combinator methods, and I have a constant for basically computing the size of the segment. It's easy to see how fragile all this code is. If I change something in my segment, if I want, for example, the array to be of 6 elements instead of 5, then some of those constants may change. And for example, if the struct of point is containing maybe longs instead of ints, then I have to consider that instead of using 4 as a dimension for the coordinates, I have to use 8 maybe on some platform, and then all the constants are going to change. We think that there is a better approach to solve this particular problem, and the approach is based on memory layouts. Memory layouts is not a new concept. I'm not inventing anything new here. This approach has been pioneered by John and others with PAC 200 in an attempt to define a very general way to capture and compress custom class file attributes. We are essentially leaning on that, and we have been leaning on that for some time inside Panama to try and capture the description of native function signatures. So we think that memory layouts here are a way to reduce brittleness of the code by reducing all these constants that we have seen hardwired in the code, by having essentially a programmatic way by which you can define or declare the structure of your memory segment and then derive all the contents out of it. So variables, offset, or whatever. And the bonus point are, of course, that since we have already used all the layout machinery for the higher level interop stuff, we know that this stuff is going to come useful later on in the game. So that seems a pretty good deal. So rather than spending too much word about it, let's see how we actually create layout. So we have our struct of point array. The way we create it is we start from the outermost layer and we create a sequence layout. Sequence layout takes a repetition count, which is 5, and then an element layout. In this case, the element layout is a struct layout. Pretty obvious from the name. And then we have to specify the two layouts of the coordinates x and y. These are two value layouts. So in the layout terminology, value layouts are leaves. So they are basically where the things that you want to access with your variables are. Sequence layouts, struct layouts, they are called group layouts. They are essentially derived layouts. They aggregate some other nested layout inside. And you can also attach names to the coordinates for a reason that will become clearer later, but we want to have a way to refer to this stuff. The way we can actually create a variable out of layout is to construct a layout path. So we start from a layout root, and then we have to find a way with our API to model a path that goes from the root to the particular leaf that we want to be able to dereference. And the rule of the game are the path has to start with a group layout, so one of those complex layouts that has stuff inside. And you can select either a sequence element or you can select a struct field, but the path must always end with a leaf. You always must end up with a value layout. So this is an example. We have our struct of point array layout, and the goal is that we want to create exactly the same variable that we tried to construct before that accesses all the y coordinates in the array. But we want to do so not by using the combinators, we want to construct it using the layout API. The way to do that is, well, there is a handy method inside the layout API that is called variable. It takes a carrier type because we want to specify what is the carrier type of the variable. In this case, it's going to be int, so we know that the type of the variable is going to be int. And if I didn't do anything else, this variable will essentially select the entire sequence, and that's not valid. I know that I need to go to some leaf. So I need to start specifying bits of my layout path. So from the sequence, I need to select the layout element, sorry, the sequence element. And since I'm not specifying any index inside the path expression, I'm basically leaving the sequence element unspecified, which means that my variable will acquire an extra coordinate at runtime. Then once I selected the struct, I will need to select which field I want inside the struct, so y in this particular case. And that's essentially it. With this method call, a path expression, I've been able to obtain the same variable I obtained before without using any combinator or any hardwire offset constant or stride constant. Everything is essentially, all the knowledge is in the layout, and I just leverage that knowledge in order to obtain a variable. And in fact, we can rewrite all the examples that we have written before, and instead of using manually written constant, we can declare the layout on top, and then we can derive the variables for the x and the y coordinates out of that. And then we can do the try with resources, we can instantiate our segment, and instead of specifying an hardwire size, we can just pass the layout to the allocator, and the size will just be derived from the layout. So that's much better than before, because there are no constants here. And the code is much more robust now. If we do a change on the layout, everything will just flow through. And everything that you see here is essentially a constant. The layout is a constant, the variables are constant. So the JIT will be able to see through all this information and optimize at will, or at least that's the hope. Then I show you some numbers and we see that if the hope is actually correct. So let's switch gears a bit and talk about the safety assumption of this API. So as I said, one of the main design decisions here was to create a safe API to access off-heap memory, which seems like an oxymoron. Of course, when you access memory of heap, you can crash everything. You can access memory out of bounds, or you can access memory that has already been freed, and there are a bunch of things that can go wrong here. How do we protect against that? And a way we protect against that is essentially by giving bounds, spatial bounds and temporal bounds to segment, and continuously verifying that the bounds are enforced at runtime. So whenever you access memory, we will do a range check to make sure that the address that you're trying to dereference is within the bound of the segment. And also when you're accessing memory, we will do a temporal check. So we will basically check that the segment is still alive, that it has not been closed. If it has been closed, you will not be given access. I know that most of you now will be pretty scared about what are the performance implications of all that, but let's take one step at a time. So in terms of usability, what this means is that, for example, here I'm creating a memory segment of 10 bytes. And I want to to set an integer starting from address 8, offset 8 of the segment. And of course, you can see that this set operation is a little bit cheeky because you start at offset 8, which is within bounds, but since I'm setting an int is 4 bytes, so it will end up at 12. And so part of it will be out of bounds. And that's the API is kind of giving me an exception, so that's good. But then I can close the segment, and I can try to do another set. And I will get another kind of exception, this time because I'm trying to access a segment that has already been closed. So the API is successful in controlling me from doing crazy stuff. That's good. So now, back to performances. How far is unsafe? So this slide could be titled The Good, the Bad, and the Ugly. So there are certainly good parts. So if you take the first benchmark and the last benchmark, everything is good. Basically, the red bar is performance with hotspot C2. The blue bar is Graal with the JVM CI option. I couldn't use, unfortunately, Graal Community Edition or the Enterprise Edition because I needed variable support. So I needed something that was greater than JDK 8. And the orange bar will show you the performance of the Unsafe, which is basically the best between Graal and hotspot. So I just wanted to have everything in the same slide. So in the first example, what we are trying to do is a get operation on a constant address. And as you can see, performance of the memory access API and Unsafe API is really the same. So hotspot is really good, and also Graal is really good at optimizing this down in the same instruction, list of machine instruction. For the last example, we have a copy, so copying a memory segment into another memory segment, and again, the bulk copy works very well. It's basically as good as a raw, unsafe raw copy. In the two middle benchmark, the situation is a little bit more complex. So in the third benchmark, the one on the right, we see that the performance gap between Graal and hotspot is very big, it's very large. And this benchmark is actually trying to, every time, allocate a new segment, do a get operation, close the segment. So there's a lot of stress on allocation. So the better escape analysis is, the better the performance is. Graal is no surprise at this particular benchmark is doing a lot better because it can take partial escape analysis to the next level. If we use some of the Panama some of the Valhalla feature and we sprinkle some of the inline classes around, we can basically reach the same peak performances as Graal within hotspot. So we kind of get in the same league. But there are also some other things that we can do in C2 in order to make performances a little bit better. For the second benchmark, though, we can see that performance is not great regardless of the compiler being used. This is a a constant address, base address, and we are basically accessing it in a loop using one of those indexed variables. So we are basically passing an argument to index different elements of an array. And unfortunately, this benchmark doesn't work very well. And the reason why it doesn't work very well is pretty trivial in a way, but also pretty complex to fix. The story here is that the Java virtual machine is very optimized to handle for loops that have int variables in them. Because the Java arrays, well, they handle int indices. Unfortunately, this API and also other APIs that we have in the pipeline, they are starting to work much more with long indices. And when you use a long index in a for loop, all the range check elimination, all the loop hoisting, the loop unrolling optimization, it will basically go away. So what we see here is that the VM is essentially unable to do any of the classic optimization on this piece of code, which means we are essentially executing a big bunch of assembly instead of just executing the raw memory access. And that's where the difference comes from. So what does that mean? Well, it means we have work to do, of course. There are some patches that we need to do to C2 in order to improve escape analysis, at least so that we can run some of the idiomatic code with the memory access API. But we have a much deeper problem with the for loop with long variables. And this is a problem on both hotspot, a little bit less so on Graal, but still a problem. And we have bugs filed on both VMs, and we will try to do better in this particular aspect. So back to safety now. For byte buffer, it's possible to create a memory segment out of a byte buffer, and it's also possible to create a byte buffer out of a segment. Of course, this comes with its own safety issues, because as you know, byte buffers are the memory of a byte buffer is deallocated when the byte buffer goes out of scope, so it's necessary for the memory segment that is created out of a byte buffer to keep a strong reference to the byte buffer, otherwise memory can go away non-deterministically. And if you do the reverse, so if you create a byte buffer out of a memory segment, well, it's important that the byte buffer keeps checking on the segment whether access is allowed, because if the memory segment has been closed, the memory may have gone away. This is a little bit harder to enforce, but as we can see in this example, it's something that we currently deal with. So here we create a memory segment of 8 bytes, then we create a byte buffer out of it, then we close the segment, and we call a getInt on the byte buffer, and we will get an exception. But if you see on the stack trace, unfortunately, the font is very small, but you can see that there is a different implementation of the byte buffer that is used here. It's called ScopeByBuffer. And it's essentially a byte buffer that still has a link to the memory segment it comes from, and it will keep checking the memory segment for permission before doing any of the dereference operation that can lead to potential crashes. So, check. Another issue, a little bit down in the rabbit hole for safety, is concurrency, of course. Yes, all this stuff works if you work in a single thread, but if you start looking at multiple threads, all bets are off. You can have multiple threads accessing the same memory at the same time, and that's kind of okay. We can basically put the cost of synchronization on the user. After all, the variable API has perfectly capable primitives in order to handle with that. But there is a more sneaky problem here, which is the access versus close race. So one thread is trying to access a segment, and the other thread is trying to close the same segment. In this case, depending on what the scheduler does, it's completely possible for a segment to believe that the segment is still open and try to access it, but in reality, the segment has already been closed. So of course we can solve this by putting a bunch of synchronized keyword everywhere and make the performance horrible. That's not what we want to do, of course. What we did for now is to stick with static thread confinement. So essentially all memory segments are statically confined with a thread. So when they are created, they have a thread owner. That thread is the only one that can dereference memory on that particular segment, and it's the only one that can close the segment. With this, we avoid most of the problems. Of course, I can hear an argument that this may be too strict for certain use cases. And I have a fully comprehensive write-up here that I encourage you to go and read that basically describes several different approaches that we can take in order to overcome this particular limitation of the API. But this is a very big trade-off between API simplicity, efficiency, and safety, essentially. So we can get a very performant approach, but we have to sacrifice some of the API usability and simplicity. If we are willing to do that trade-off, then there is a path there. Another thing, very cheap thing that we can do is also to maybe add a method on Unsafe and create a racy segment. That's a very simple solution for people that really need to do that particular kind of thing. But we believe there's also a safe API that we can expose here. So, concluding, the memory access API is the missing primitive for Panama. It's something that once we have it, we can build all the stories, all the higher level interop stories on top. We can build method handle-based foreign function calls, and we can build jextract high-level APIs on top. The memory access API, as I hope I have convinced you, is a safe API. So a lot of design cycles have been put in order to make sure that you cannot accidentally crash the VM by using the API in some crazy ways. And the API is also efficient. At least we try to make it as efficient as possible by co-designing the API together with JIT engineers. So we are open to suggestions to make it faster, but as you have seen, we have work in the pipeline to make this as optimized as possible. So our goal is really to make it as fast as Unsafe in the vast majority of cases. And I think we are kind of 60, 70% there. There's more work to be done, but I think we will get there. So these are a bunch of links. The code repository with the foreign memory access branch contains all the code for this particular API. There is also a Java doc that they made available. We did a bunch of review iteration on it. We think it's fairly 80% review ready. So if you want to take a look at the API, I think now it's a very good time to do so. The next step is essentially to round up the performance work, and we actually would like to, I already have a JEP in the pipeline, and we would like to make this available as an incubating module as soon as possible for people to try it out. Because of course, we need also to know from people whether this API is working well for them. And next step is, of course, to shift gears and start to focus on the higher level interop stories for Panama. So this is something that is already happening if you are looking at the Panama dev mailing list. So we are already starting to build the ABI support on top of this API, and we will continue to do so, I think, for the next few months. That's the slide. Thank you very much.